Hey, this is Mr. Mitchell with another video. Here are some questions, and you can see from the questions it's going to be about waves. Here are some wave characteristics. If you were to take some kind of buoy out in the water and see it in a storm, the buoy at the top of the wave would be way up here, and then it would go down, and then the buoy would be at the bottom of the wave, and then it'd go up, and then the buoy would be kind of in the middle, and then the buoy would be at the top of the wave again. And you know what's coming in are the waves in the ocean, and you could actually plot these on a graph. You can see this is like on graph paper. But there are some terms that kind of go with this. Every wave, every transverse wave, oh, what am I doing? Every transverse wave, you can actually make a plot out of this. It doesn't have to be a wave like in the ocean. If you have a transverse wave, you can make one of these, and these are called sine curves or sine waves. And with every wave, whether it's a radio wave, whether it's a longitudinal wave, or whether it's a transverse wave, you have kind of terms that go with it. Now this is going to be transverse here, but I'll show you a little bit about longitudinal in a little bit. These transverse waves, the highest point is going to be called its crest. The lowest point, well, I bet you can guess this one, is going to be called its trough. And the amplitude is going to be the measurable distance between the line right in the middle of it, which if you graph it would be the x-axis, and the top or the bottom, and it should be the same measurement. So this measurement from here to here would be the amplitude, and it should measure the same all throughout here. The amplitude is from the line through the middle, or the x-axis, all the way to the crest or to the trough. That's what the amplitude is. Now down here we've got one of these longitudinal waves, and you can see I've got some terms that are right beside it. The terms are compression and rarefaction. The compression, well, this was kind of like a slinky. Kind of like a slinky. You may remember we mentioned it, I think it was even in the last video. There are areas where it's just not quite as wide as others. And like right here, you can see there's not much space between this. Of course, is the compression. What in the world was that? Well, anyway, I'll just let it be on this video, whatever it was. Next is going to be rarefaction, which are these places where you do have a lot of space in between. In fact, I think I see rarefaction is mentioned down here. Now, we'll probably come back to this longitudinal wave. So these are some terms I'd like for you to know. And they kind of lead up to these bigger terms: wavelength, period, and frequency. Let's talk a little bit about wavelength first of all. The distance from one wave crest to the very next crest is called the wavelength. So from crest to crest, you have a distance. The distance is actually measured in meters. Now, with some waves are very, very small, so it's going to be very, very small amount of meters, even way below millimeters. But you know, the standard SI unit is going to be meters. So wavelength is going to be distance in meters from crest to crest. Now that will actually be the same distance from trough to trough. So if you happen to see that definition, use trough to trough, it's going to be the same thing. And there's actually a funny little symbol for wavelength. It looks like an upside down Y, probably a Greek letter. But anyway, that is what the wavelength is. The period is going to have to do with this distance also, but the period is how much time it takes. The time it takes for one wavelength to happen. The time from one top of the crest to another. And with some waves, it's actually going to be longer than you might think, but with most of them, it's going to be a very short period of time. Frequency. Frequency is the number of waves passing a fixed point in a certain amount of time. You know, the word frequency comes from frequent, and frequent means often. So I guess you could say that frequency measures how often a wave occurs. So the frequency we look at like a fixed point. So how often does the wave go through here? Once, twice, 3 times, 4 times, and so on and so on. So it's going to be measured by the number of crests or troughs that pass by in a given second. So it's kind of like taking wavelength and putting it over time. So wavelength over the period, which is measured in time, is going to be roughly what the frequency will be. You can see frequency is kind of a elongating looking F. So wavelength over time will give you how often it will happen on any given time. Now you know from the definition I read that they like to have it from the crest and from the trough because you don't always have this little line right here. So you can actually do some calculations with wavelength and frequency. But before we go to that, let's go back to this earlier slide. You can actually take a longitudinal wave like this down here and make it look like this wave up there. The compressions will be where the troughs are. So you could literally have one go dip at the compression, go up at the top of the rarefaction, dip at the compression again, and so on and so on. So it's really not that hard of a process in which to do that. So you can have a longitudinal wave and still end up having the measurements of wavelengths and period and frequency. Now look down here, we have radio frequency, which is very, very fast. And we have some radio frequency which is very, very slow. Now I want to kind of point out something. Oh, well, here's this. Should have just watched that right there. I want to kind of point out something, that whenever you have it going very, very fast, your wavelength is small. Your wavelength is going to be small. But what can you say about the frequency? Do you have a lot of frequency? Yes. You have a lot of frequency. So whenever you have a small wavelength, you have a lot of frequency. Now look down here. Here we have the wavelength, which is relatively big compared to what it was here. So would you have a lot of frequency? Does it often come through the top here? No. So it's just the opposite. So you could say that in this case, the wavelength is going to be big, but the frequency is not going to be big. It's going to be small. So it's kind of like you may have heard the term in math, an inverse. So you kind of have an inverse property. If you have a small wavelength, you're going to have a big frequency. If you're going to have a big wavelength, you're going to end up having a small frequency. And that's kind of the nature of that. Well, you know there's going to be a formula just because this is physics. But anyway, here's the formula for wave speed. V is going to be for speed, and I take you back to way back at the beginning of the course when we mentioned speed and velocity. In this case, you know, normally velocity has a direction to it. I think it's kind of understood that waves will have a direction to it, that you're not going to go one direction and then come back another, and so on, that it's all going to be going in one direction, whether it's left or right across the sine curve. But anyway, here's the wave speed formula. It's a pretty simple one. You have the frequency times the wavelength. Now keep in mind, if you have a big frequency, you're going to have a little wavelength, and vice versa. If you have a little frequency, you're going to have a big wavelength. So you're often going to find things like this. Here you have a big number for frequency. A tuning fork has a frequency of 310 waves per second. And you have a small number for the wavelength, 1.32. So that's going to happen in almost every calculation you have. You're usually not going to have these incredibly large numbers. You're going to have one large and one small. Now, you're going to end up finding out probably when you take this course in high school that waves per second is going to be in something called hertz. We just won't have that in this class, though. You'll get that later on. So if wave speed equals frequency times wavelength, wave speed equals, let's say the frequency is 310. That'd be waves per second times 132 meters. So 310 times 130, or 1.32, I should say, 1.32 is this. 3. Okay, come on, computer. Clear it. 310 times, what was that again? Times 132. 310 times, I'm sorry, times 1.32. So let's see what that comes up to. 409.2. And you may wonder what the speed is going to be in. 409.2. I can tell you what it's going to be in. It is going to be in meters per second. That's good because that's kind of what velocity and speed is typically measured in anyway. Well, I hope you can remember some of this stuff, and if you don't, then you can always come back and watch it again. Don't forget the questions.